Hello everybody, welcome to this first interactive session for Introduction to Solidification Processing. I hope you are enjoying this particular course. And this course is basically intended to look into typically the thermodynamic principles, starting with that different phase transformation related issues. Then we'll try to discuss the principle of solidification, and then applications of these things, solidification in casting, and finally solidification in welding and additive manufacturing, and try to focus on the different solidification techniques. So these are the overall structure of this particular course. But we of phase transformation, and in this case, probably most of the content you have studied in your basic thermodynamic course, and from there you just try to utilize this relation, this understanding to explain the solidification behavior or application of the solidification application to understand the solidification processes. So far, I have not found any kind of the questions raised by the attendant who is basically following this particular courses. So I have decided to present the very basic things in a more simple or simplest way to understand the particular topics associated with this subject. So if we look into the syllabus for this subject, it starts with the introduction to the phase diagram, then equilibrium, single component system, binary solutions, then heterogeneous systems, diagram, phase diagram, binary phase diagram, and understanding of the interfaces, then kinetics, phase transformation, and finally simulation or demonstration with an examples to understand all these thermodynamic principles associated with the phase transformation. So this is the very basic learning of the solidification processing course. And then we'll have the principles of solidification is basically having the nucleation in the pure metals, what the different types of the nucleation occurs, growth of the pure metals, solidification of the alloy, eutectic solidification, and simulation of the nucleation and growth to understand in a better way the solidification processing associated with the different manufacturing processes. So mainly the manufacturing processes, casting and welding, we can find out the applications of the solidification processing. So with respect to that, here I hope up to this point of time, probably we have covered up these first two modules, this thermodynamic principle of the phase transformation as well as the principle of the solidification has been covered up. So I'll try to focus on some selective content in particular to this two different modules. Now, questions for live interactions. Found no questions raised till now along with this live interaction session. But anyway, I'll try to discuss the very basic things so that you can understand the better way the subject. The recommended books for this particular course is given. This first one is the phase transformation in metal and alloy. That is a very good book if you try to understand that what the thermodynamic principle is applicable to understand the phase transformation. So the first book is the very informative or very fundamental studies are available associated with these books. So you can go through this particular book to understand the first module. Then of course, fundamentals of solidification also details different this next book that is also useful to understand the different concept associated with the solidification processes. And finally, application of these things in castings. You can go to the third book. If you understand the heat transfer phenomena associated with the metal casting process, the book number 4 is very, very useful. And if you understand that welding metallurgy, which is basically more relevant to the solidification, heat transfer and solidification associated with the welding process, that is book number 5th book is more useful. And finally, 6 books in general, if you are very interested in the physical metallurgy. So fundamentals of the physical metallurgy is basically explained in the 6th book. So these all 6 books are basically useful to understand the complete syllabus of the introduction to the solidification processing. So anyway, here the solidification processing, we basically have discussed only the introductory level, but just to understand the basic concept associated with this process. Now, what way the thermodynamic principle is helpful to understand the equilibrium. So to understand the equilibrium in a particular system, we understand when it is basically reached to the most stable state, but how you can define the different stable state, which parameter is basically responsible to understand mathematically that we are reaching the stable state. In general, a constant at constant temperature and pressure, a closed system will be stable equilibrium if it is having the lowest possible value of the Gibbs free energy. So basically, this Gibbs free energy, this parameter we are using, or we are to understand to the equilibrium state of a particular system. Now, Gibbs free energy, absolute values of the Gibbs free energy can be explained like that: G equal to H minus Ts. Now, mathematically, when this perform change of the Gibbs free energy at constant temperature is happening, then we can find out, we can say that dg equal to dh minus t into ds. Now, here I can see that when system reach the stable equilibrium conditions, or I can say the very local equilibrium condition you try to reach, then in that cases, dg equal to change of the Gibbs free energy should be 0. It means that it is locally reaching to the equilibrium conditions of the thermodynamic system. Now, in the thermodynamic system, when you're reaching the equilibrium, so from the expression itself, we understand the highest stability. Stability means the minimum value of the G. So that can be achieved either two different, either reaching the minimum value of the H. H means basically enthalpy of a system, or highest value of the entropy. So both way we can reach the minimum value of the Gibbs free energy. So it's basically, we can say the high stability is basically compromise between the low enthalpy and the high entropy. So that combining these two basically try to reach the lowest values of the Gibbs free energy, or I can say that try to reach conditions for reaching the stable equilibrium positions. Now we can further explore this particular phenomena to understand the equilibrium of a thermodynamic system. That G equal to H minus Ts, of course, this we know, the expression of the Gibbs free energy, and enthalpy H equal to E plus PV. E is basically internal energy of a system, and pressure and the state of the pressure and volume of this particular system. Now you can see that at low temperature, usually can see the solids are more stable because they are having the strongest atomic bonding at the low temperature. So it means that the strongest atomic bonding or solid phase are stable. It means that lowest values of the internal energy, or I can say that enthalpy of the system is the lowest in case of the solid phase. Now, when we reach the very high temperature, the elevated temperature, in that case, the entropy terms actually dominates. And in this case, phases having the more freedom to the random movement of the atom. So it means that the entropy becomes very high at high temperature. So that's why at high temperature, the liquid and gases become more stable. So what we can say, and that is very relevant to this expression, G equal to H minus Ts. So what we can see that trying to reach the lower values of the enthalpy, which means the lowest internal energy of a system, and that is the one way to reach the stable state, and that is true in case of the solid phase. But in case of the liquid or gaseous phase, that in that case, the entropy becomes very, very high at high temperature. So in that case, with the entropy becomes very high. So liquid and gaseous phase is actually very more stable at the high temperature. Now, independent of these two parameters, enthalpy and entropy, we can see that if all these cases we are keeping that at constant temperature and pressure, but if pressure changes are considered, if there is a change of the pressure of a system, in that case, the phases having the small volumes, they actually are favored to reach the equilibrium by the application of the high pressure. So these are the typical conditions to reach the equilibrium state of the solid phase or system, usually having at the very high pressure. In that case, we can reach the small volume part, which is try to reach the equilibrium condition. So therefore, mathematically, you can say the stable equilibrium means dg equal to 0. That means change of Gibbs free energy equal to 0. Now dg can be 0. If you look into this figure, the two different configurations of the atoms. So for example, configuration B and configuration A. Both the cases, dg equal to 0 in this case. We can say that state B is the local minimum of free energy, is basically reaching, in this case, dg equal to 0, but may not have the lowest value of G. There might be some other meta state where we can reach the lowest value of the G. So that is the in condition for A. Although local equilibrium is there, local minimum and free energy is there, but it is a more stable state as compared to the state B. It means that, of course, B and A holding the different arrangement of the atoms. So therefore, we can say that intermediate state where dg not equal to 0, these are basically unstable state due to the thermal fluctuations. In that case, if the atoms arrange in an intermediate state, but if they are rearranged into one of the minimum free energy state, such that we will try to raise the value where dg becomes change of the free energy equal to 0. Now, if there is a change in the temperature or pressure, in that case, our system try to move into another equilibrium state, or I can say that another metastable state over the time. Now, but over the time, it is gradually try to transform to a stable equilibrium state. So these are the physical phenomena associated with any kind of the state of the equilibrium in a thermodynamic system. So I mean to say that, so different atomic arrangement are possible, say for example B to A, but of course they are trying to reach the local equilibrium state, but in between they will try to different metastable state, but over the time, at a certain point of the time, it always try to give the from metastable state to very stable equilibrium state. It is possible. So this is the basic understanding of the equilibrium state of a thermodynamic system. Now, if we look at the single component system, here try to understand how the enthalpy and G basically Gibbs free energy is basically changing temperature, because we define that the state of the phase, basically solid phase or liquid phase in terms of temperature. So that's why here you can see that enthalpy for the dotted line is basically for the liquid phase, the enthalpy H. So that is basically gradually increasing with respect to an increasing temperature. And when there is a change of the phase from solid phase to liquid phase at the melting point temperature, then there is that it follow change in increment of the there is a from solid phase to liquid phase, there is increment of the enthalpy. And similarly, if we follow that free energy, G value gives free energy with reference to the temperature, with respect to the temperature, we can see that the minimum value is there, the solid phase before melting point temperature. But when it is crossed the melting point temperature, in that case, the minimum value is basically for the liquid phase. So that actually transition zone is basically decided by the melting point temperature. So, and at the same time we observe, now what are the observation from this graph is that Gibbs free energy is always in the values in the negative. Okay. Now at any temperature, definitely liquid has higher enthalpy than solid. From this graph, it is very much obvious that at any temperature, the enthalpy of the liquid phase is more than that of the solid phase. But at the low temperature means below the melting point temperature. Here we can see that enthalpy G for the G for the liquid phase is basically greater than G for the solid phase. So basically solid phase having the lowest negative value of the Gibbs free energy. So here that is obvious from this graph. But liquid phase has the higher S entropy than the solid phase. That is obvious because the atomic arrangement or atomic attraction are different. Basically, in that cases, randomness is much more the system at the high temperature. So therefore, liquid phase having the higher entropy than the solid phase. And G for the liquid phase decreases more rapidly. You can see the slope. So here G for the liquid phase, that means Gibbs free energy for the liquid phase is very rapidly decreasing with increasing temperature. It means that more rapidly decreasing for the liquid than solid. So slope is much more for the liquid phase than solid phase. But up to the melting point temperature, solid phase has the lowest G. That means solid phase has the lowest values of the Gibbs free energy. But it means that these are in the stable equilibrium phase, because Gibbs free energy is the values is the lowest in this case. But above the melting point temperature, in that cases, liquid phase is in equilibrium, and we can say when liquid phase in equilibrium, it means that liquid phase having the lowest value of the G above melting point temperature. But at melting point temperature, both the phase having the same values of the G. So solid and liquid phase is actually in equilibrium conditions at this particular point. So that means melting point. So that's why phase transformation occurs at this particular temperature. So these are the typical observation from the single component system, how the enthalpy and Gibbs free energy is varying. Now, if we look into the other aspect of the single component system, at very high temperature, the free energy of the gas phase, basically, or even it is in atmospheric pressure, it actually becomes lower. So free energy for the gas phase becomes lower, because at the high temperature, gas phase becomes more equilibrium condition when it is having the lowest values of the free energy. And it is lower than that of the liquid, as well as the lower than that of the liquid. So in that case, it means that the liquid is transformed to the gas by lowering the free energy. And then it means that when it is lowering the free energy, so therefore liquid phase is, gaseous phase is more stable than the liquid phase at the elevated temperature. Similarly, the solid phase may also exist to the different crystal structure, that is known as the allotropic or polymorphic form of the any component. So in that case, definitely when the same solid, but they are having different crystal structure, different phases, solid phase coexist. So in that cases, their free energy curve will be different. Now, when the free energy curves intersect at a particular temperature, it means that equilibrium temperature for the allotropic transformation. It means that if it is a, for example, if it is a solid phase to transforming the liquid phase, so basically both are equilibrium at the melting point temperature. Similarly, when this indicates the equilibrium temperature at particular when they are intersecting, the free energy intersecting one particular point, so that's it means that one phase is transformed to the another phase, or both the phases having equilibrium temperature. So their example is that, for example, at atmospheric pressure, iron has BCC ferrite below 910 degrees centigrade and FCC austenite above 910 degrees centigrade. So therefore, at 910 degrees centigrade, both the phases can exist at the equilibrium condition. So this is just an example of the two different solid phases, but their free energy curve will be different, and their both will be equilibrium at the when they cross the two G curve cross at this particular point. So that point, both are in equilibrium phases. Now we try to look into that nucleation in the pure metal. That means solidification. That is one of the most important or main part of the solidification processing. Is what way the solidification occurs. So we can explain the solidification occurs in the two different phases. One is the two different stages, nucleation and growth. And in this case, two stages, nucleation and growth. So nucleation is basically appearance of the very small particles or nuclei of the new phase. So it means that nucleation occurs means from it's a appearance of the new phases, or in this case, very small particles is basically creates from the, for example, solid phase is basically creating from the liquid phase, and in the form of a nucleation. So that means it is basically new phases has been created. Now, once the nucleation occurs, then after that we'll try to, when favorable condition arises, then nucleation sustain, and then you try to grow and following the growth phenomena associated with any solidification process. So once nucleation occurs, but two types of the nucleation usually occurs. One is the homogeneous nucleation, another is the heterogeneous nucleation process. Now, we know that homogeneous nucleation process is the nuclei of the new phase occurs uniformly throughout the structure, parent phase. So each and throughout the parent phase, the nucleation occurs, new phase occurs, so that is known as the homogeneous nucleation process. But if nucleation occurs with a predefined or preferential as a particular site, in that case, we can say the heterogeneous nucleation occurs. So it's basically some pre-existing sites, which is basically create the nucleation or favors or the nucleation to occur, because of in that case, the amount of the energy or energy barrier in the basically lower than that of the homogeneous nucleation process. So heterogeneous nucleation process, we need some pre-existing surface is required to start the heterogeneous nucleation process, but that is not the condition in case of the homogeneous nucleation process. Now we can explain the nucleation in the pure metal. So therefore, during the solidification, the atomic arrangement actually changes from a random or short range order to basically long range order or crystal structure, that we can see how the nucleation occurs. So nucleation occurs from the very start, the forms from the liquid phase, and then nuclear grow, and atoms from the liquid phase are attached to it. And in that case, of course, it needs to overcome the free energy available as a driving force to start the nucleation process, and other side, if what is the amount of the energy required to form a new surface, because from liquid phase to solid phase when it's transforming, so change of the phase is there, but at the same time it is creating the new surface. So some amount of the energy will be required to create this new surface. So therefore, what is the available free energy? A balance should be maintained. What is the in terms of the available free energy with respect to the energy consumed forming the new interface. So combining these two, then nucleation usually forms. So now here it is very important to know that once the rate of change of the free energy becomes negative, that means change of the free energy, rate of change of the free energy becomes negative. In that case, that an embryo can grow. So that is the favorable conditions to grow the embryo. But it is also important to know that what can be the size, initial size of the nucleus, such that this particular nucleation will occur. So that can be decided in terms of the free energy required to a critical size of the nucleation, such that the nucleus, that if the amount of the driving force is available, which is reaching to create that critical size, then some nucleation, that particular nucleus will sustain. Otherwise, it will again dissolve if it is lower than this. So basically, you need to overcome some critical amount of the energy is required to start the nucleation process. Now, how you can estimate this critical amount of the energy? So here we can see that nucleation in the pure metals in this way. So if you follow this figure, and we can see that is the very small temperature range. If we plot, x-axis is the temperature and y-axis is the Gibbs free energy. So that we have already explained how the Gibbs free energy changes for the liquid phase and the solid phase. So liquid phase having the higher slope, this is the Gibbs free energy change, Gibbs free energy, and the solid phase, because below the melting point temperature, solid phase is more stable, so more negative value for the solid phase. And in this case, we are following this way. So, or I can say that solid phase Gibbs free energy is lower, and the liquid phase, the Gibbs free energy is the higher below the melting point, before the melting point temperature. Now, at a particular point, this is the, if we see at a particular temperature T, and that T is below the melting point temperature, lower than the melting point temperature, and at this particular temperature, the free energy change is available equal to delta G. So that is graphically you can observe this free energy available for the delta G, and corresponding degree of undercooling to the system equal to delta T, which is deviated from the melting point temperature. Now, this Tm with reference to the melting point temperature, below that solid state is more stable, beyond liquid phase is more stable. So that we have already observed from this analysis. Now, how you can calculate is the energy of fusion. So delta G, here you can see the delta G equal to delta H minus T into delta S. That we have already seen that from the Gibbs free energy equation, the enthalpy, change of enthalpy at a particular temperature and change of entropy. Now change of enthalpy is equivalent to the latent heat also. So latent heat L minus T into delta S. So delta S can be calculated, I think in this case, that if you look into the delta S, can be calculated L by Tm. We are coming this how the delta S becomes L by Tm. So suppose delta is equal to L by Tm, and from here you can find out L into Tm minus T by Tm. So that is basically L into delta T by Tm. So basically delta G gives free energy. In this case, change of the free energy change is basically equivalent to the latent heat, change of enthalpy delta T, degree of undercooling available at melting point temperature Tm. So this is the expression for the change of the things before the change of the free energy change in this case. Now at equilibrium melting temperature Tm, the free energies of the solid and liquid phase are equal. So at melting point, we have already explained, at melting point temperature, free energy for the both the solid and liquid phase there should be the same. So it means that delta G equal to 0. So delta G equal to 0 means here we can put the expression delta G equal to delta H minus Tm into delta S. Here delta G equal to 0. So therefore, and delta G equal to 0 at temperature T equal to Tm at melting point temperature. So let me make it 0. So here we can say calculate the delta S equal to delta H by Tm. So delta H is basically equivalent to the latent heat L by Tm. So from here you can see the L by Tm, put it, and we are getting this calculation. And here delta S is known as the entropy of fusion. So this simple calculation, you can find out the entropy of fusion is basically simply at melting point temperature L by Tm. And we can easily calculate what is the driving force or free energy change is required in this that is the at temperature which is close to the melting point temperature that we are about to finish. Now, when you're looking into the homogeneous nucleation process in case of the pure metal, so we start with the element having or filled with the liquid phase. So here fill in the liquid phase, and we know that delta G equal to L delta T by Tm that we have already discussed. And here the volume free energy delta GV equal to LV delta T by Tm that can also be here. Now, what is the absolute values of the free energy available at the liquid phase? So here you can assuming that liquid phase G1 free energy available Vs, the solid phase, which is same volume equivalent to the same volume, which is basically assuming that volume is creating the nucleus. So basically nucleus volume is Vs here, which is included here, and remaining volume is the VL. And initially all are liquid phase, therefore Vs and VL is the total volume of the liquid phase here, and multiply by the GVL. So free energy for volume free energy for the liquid phase. So that's why multiply by the GVL. And this is the status of the value of the free energy available for the liquid phase. Now, suppose there is a change of the free energy state G2 equal to G1 plus delta G. Now, what can be the G2? And this G2 is basically, we are assuming there is a nucleation form. So some liquid phase converted to the solid phase and having some spherical shape, size, and that creates some kind of the interface. And we can estimate that if it is a spherical shape, we can just know the volume of this nucleus equal to 4 by 3 pi r cube, and the surface area is basically 4 pi r square. And gamma SL is the surface energy, and delta GB the volume free energy. Now we can calculate G2 equal to from here G2 equal to status of the gives free energy at state 2 Vs into GVS. Vs is the volume of the solid phase, and its amount of this volume free energy GVS equal to plus VL, the volume of the liquid phase, and then here the free energy volume free energy GVL, so free energy associated with the liquid phase, and new surface is there. So SL is the surface area into the surface free energy gamma SL. If we calculate this thing, now we can calculate what is the total free energy change from G1 to changing to reaching to the phase G2, one phase to another phase. So we can say the total free energy change delta G equal to G2 minus G1. So G2 minus G1, we put this expression here, G2 minus G1. Then we can find out Vs, GVS minus GVL plus ASL gamma SL. So it means that GVS minus GVL. So GVS solid phase free energy and GVL equal to the liquid phase free energy. So change of this thing, delta GV is corresponds to the negative value that we can see the absolute how the liquid phase free energy change that gives free energy changes for the liquid and solid phase. From there we can find out this is the free energy change should be the negative here. So delta GV minus of Vs into delta GV plus ASL, gamma SL. So these things we can calculate, and now Vs equal to the solid area of this thing, sphere, the nucleus size of the nucleus, 4 by 3 pi r cube, delta GV plus 4 pi r square, gamma SL. So you mean to say that total free energy change of this system when there is a formation of the nucleation, you can see that volume free energy changes negative way, and the surface free energy actually increases positively. So of course it proportional, its surface free energy is basically proportional to the r square, but volume free energy proportional to the r cube, but that is decreasing. Now from here we can see that when r is smaller than some critical value, so I assuming this is the nucleation occurs, this by defining the size of the nucleus, definitely it is having some critical value, say r star. Now suppose radius is smaller than the some critical value, so therefore increase the r, it basically leads to an increase into delta G. So that means the total free energy change is increasing order. So when total free energy is increasing order, that means the system is not stable. System becomes unstable. But in other way, if R value radius is higher than the critical value, it means that an increase in that actually try to decrease the volume free energy delta G. So when there is a decrement of the volume free energy change, it means the system becomes more stable. So I mean to say that there must be some values of the critical size. Beyond that critical size, the system will be stable, but lower than the critical size, the system will be the unstable. So that is correspond to the critical size of the nucleus. So, but we can calculate what can be the critical size of this. So here we perform the differential of free energy change, delta G expression, we can find out the free energy change differentiation, and from there we can get this value equal to 0, and derivative we perform, and we can find out the critical size of the nucleus. So critical size of the nucleus depends on the what is the surface energy for creating the new surface energy required, plus delta GB, the what is the volume free energy change. So that ratio is basically indicates the critical size of the nucleus. And in terms of the degree of undercooling, latent heat, in terms of this melting point temperature, we can further, because delta GB, we can calculate the delta GB here. We have already seen delta GB, volume free energy change, corresponds to the ALV in delta T by TL. So use this expression, then we can, in terms of that, we can find out the critical size of the nucleus. Now, similar expression, we can calculate what is the critical energy barrier associated with the homogeneous nucleation process. And that also we can calculate in terms of these parameters. And if we try to follow the graphically represent these things, that volume free energy is basically here it's volume free energy decreasing proportional to the r cube delta T, and interfacial energy is basically increasing proportional to the r square. And then combining these two, the curve is in such a way that it is basically gradually increasing, reach the optimum point, and then it is decreasing. So that is the amount of the critical energy barrier, that optimum point, that is the required energy barrier, and corresponds to the critical size of the nucleus. And this is true in case of the homogeneous nucleation process. It means that there is no other external aid to start the nucleation process. So these are the typical understanding of the nucleation in case of the pure metal. I can say the homogeneous nucleation process in case of the pure metal. Now, if we try to look into the nucleation process in the heterogeneous nucleation process, we can see that we start with the liquid phase is there, but there is some nucleating agent, but some external surface is there that actually initiate the nucleation process. So that's what is known as the heterogeneous nucleation process. So in this case, we can perform the similar calculation, a similar strategy you can follow. So what is the Gibbs free energy at G1, state G1 and state G2? And then we can find out what is the difference between the G2 and G1. Then we can find out this expression. Now, if we do that, we can see that it's a similar kind of the expression is available. Delta G heterogeneous equal to this corresponds to the homogeneous into S theta. Now, this shape factor S theta, how it is coming here, because in this we can see that the solid phase is grow over the pre-existing surface. So it's making a particular, when it is in equilibrium and making a particular, but it cannot follow the complete spherical shape because there is a pre-existing nucleating agent is there. So therefore, suppose part of the sphere it will create it, and that is the size of the nucleus, and that suppose the weight, depending on the weightability, the angle equal to theta here. And then we can see there is a surface tension between the two medium. So that means the between liquid and solid, and between the nucleating agent and solid, and between the nucleating agent and liquid. So these are three different, the surface energies are available because there are three interacting surfaces are there. So that's why three different surface energy are there. And then in that cases, we can make the balance also, making this particular angle theta stable. So gamma ml x component and gamma sm, the x component out, that should be equal. And of course, the component of the gamma SL along the x direction, that should be equal. So if you consider all this type of calculation, then you can reach this expression where S theta is the one shape factor will be coming into the picture. Now S theta can be expressed like that, and S theta equal to in terms of the theta 2 plus cos theta into 1 minus cos theta square by 4, and this S theta will always be less than 1. It means that what is the free energy change for the heterogeneous nucleation, which is always less than that of the homogeneous nucleation process. Now, if we follow this calculation, critical value of the critical size of the nucleus, and what is the critical values of the free energy change, then we can see the right hand side graph. Graphically, we can represent these things, homogeneous and heterogeneous, both the cases. We can see that critical size of the nucleus is the same for the homogeneous and heterogeneous nucleation process, but the energy barrier required for the homogeneous nucleation process is much more than heterogeneous nucleation process, because here the heterogeneous nucleation process we are having the pre-existing surface, and that can be represent this thing, similar expression you can use, multiply by the S theta, and you can see that the R star is basically independent of the shape factor S theta. So that's why critical values of the nucleus is the same for the homogeneous and heterogeneous nucleation process, but delta G star will be always less than that of the homogeneous nucleation process. But this model actually does not work when theta equal to 0 degree. So that value is there. So I think that's all. So here I have tried to explain the basic, very basics associated with the solidification process, the homogeneous and heterogeneous nucleation process, and what we can understand the equilibrium condition in terms of the Gibbs free energy in case of the, or I can say in terms of the different phases, the equilibrium condition, what we can explain using the free energy chain. Thank you. Now, if you have any questions, maybe you can raise these questions now, or you can type in the chat box if you have any query related to this particular course. If you don't have any questions, okay. You have any questions, maybe you can post it. Sanjay Basumatari, any questions? Do you have any questions? Okay. So I can stop here. Maybe you don't have any questions. So I don't found any queries or any questions. So I can stop here. Okay. So madam, I'm leaving this site then.